Hey guys, I have absolutely nothing planned here, but I'm going to try to go through some. I just got home and I was like, okay, I'm going to try to knock out a few of these. So, we're going to talk about 8.4. This is where we had a few different things. We had the ratio, we didn't have the ratio test. We had the direct comparison test and we had the limit comparison test. The direct comparison test, you guys have this simple kind of concept of 0 is less than a sub n is less than b sub n. And you pick a series that either converges or diverges and then show that the function's either always smaller or always larger. If b of n converges, the series that you pick, and we know a sub n is always smaller, then a sub n must also converge. And we know that if 0 is less than a sub n is less than b sub n, and you pick a sub n, if a sub n diverges, and you know the series that you're looking at is always larger, then b sub n also must diverge. Okay? The second part, when you guys are talking about this, we have the limit comparison test, and this states that if the series is positive, continuous from 1 TINUOUS from 1 to infinity, all positive integers from 1 to infinity. And if it's decreasing, then we can go ahead and apply this part right here, I believe. Wait, no, that's for the integral test. For the limit test, all we have to do is go through and take the limit as a sub n divided by b sub n. If it's equal to some number that's positive, that's why I thought it was this one, excuse me. If it's positive, okay, and finite, positive finite number L, then we either say that both diverge or both converge. It's one or the other. So you pick something to compare it to that you know converges or you know diverges, and one of them is going to produce one of these finite positive values, and then you can go through and determine that. We generally pick the limit comparison test when we want to go through and we want to prove it for a crazy function or crazy series. And we want to go through and do the direct comparison test when there's something that we know that kind of looks like something we already have. So what we're going to do is go ahead and start out. We're going to go through like number 13, 15, some number between 27, 34, and then we'll do like 71. We're just going to pick out like 4 or 5 of these and go through it. So let's start with number 13, okay? Number 13, when you guys are looking at this, it says we're going to be using the limit comparison test. The limit comparison test, when I'm looking at it, I know that this looks like n over n squared. So I know that I can compare to n over n squared, which is 1 over n. So what I'm going to do is say that this is b sub n, and this is a sub n. And all I need to know is that if I take the limit as n approaches infinity of a sub n over b sub n, it has to be equal to some finite positive integer. It cannot be 0, it cannot be negative, okay? And so what ends up happening here is I get the limit as n approaches infinity of n over n squared plus 1. I'm going to put parentheses around this because we're going to be dividing fractions. Over 1 over n. And when we divide fractions, we're going to end up multiplying by the reciprocal. So we're going to take the limit as n approaches infinity of n over n squared plus 1 times n over 1. Okay. What's going to happen here is I'm going to get the limit as n approaches infinity of n squared over n squared plus 1. If I do this, I'm going to end up getting infinity over infinity. This is going to approach infinity right here. Infinity. So what that means is I have to apply L'Hopital's rule, and I'm going to get the limit as n approaches infinity of 2n over 2n, which is going to be equal to 1, because 2n divided by 2n is 1. So what this means is both converge or both diverge. Okay. And then, so what we're going to go through and say is since the sum from n equals 1 to infinity of 1 over n diverges, then the sum from n equals 1 to infinity of n over n squared plus 1 also diverges by the comparison test, by the limit comparison test, LCT or limit comparison test. Why does 1 over n diverge? This is the harmonic or the p-series where p is equal to 1. This is harmonic. You can simply state that it's p-series where p is equal to 1, or you can just say it's harmonic. Either one will work on the AP exam. Okay. When we go through and look at other ones of these, number 15 follows similarly. Number 17 I can already tell is gross. But we'll go through and knock out number 17 doing the same thing, okay? We've done a lot of comparison tests. We haven't done as many limit comparison tests. So let's go through and we'll knock this one out as well. We're going to compare to, we want to match the highest power exponent on top and bottom, so n squared over n to the fifth. We know that this is going to reduce down to 1 over n cubed if you subtract the exponents. So when we do this, we're going to take the limit as n approaches infinity of 2n squared minus 1 over 3n to the fifth plus 2n plus 1. And we're going to divide this by 1 over n cubed. And if this gives us a positive finite number, we know that both are going to converge or both diverges. This one converges when you take the sum from n equals 1 to infinity of 1 over n cubed, because it's a p-series where p is greater than 1. Okay? We have a p-series where p is greater than 1. So it works out perfect. It converges. So if this gives us some number, then it also converges is the basic idea. So what we're going to do is multiply by the reciprocal. We're going to get the limit. Opal, you got to give me a minute, girl. I'm almost done. I know you want to play. It's okay. My dog's trying to lick my face right now. I don't like her licking my face. All right. Good girl. You're a good girl. All right. Times n cubed over 1. And when we do this, you're going to start to see that we're going to get the limit as n approaches infinity of 2n to the fifth minus n cubed over 3n to the fifth plus 2n plus 1. And I don't know if you guys saw it from the last one, but as you take L'Hopital's rule, the only thing that really matters is the coefficients that are in front of these. So if we're looking at these, we have 2n to the fifths. If we go through and take the derivative another 3 times, we'll have the tops cancel, and we're just going to be left with their coefficients, which in this case, it's going to go and approach 2/3. If you don't believe me, go through, apply L'Hopital's rule 3 times to cancel out this n cubed. And once you finally get there, you guys are going to see what it approaches. You're going to have to do it 3 or 4 times. I think the 4th time is going to be the charm, and you'll get 2/3 still. So what does this mean? It means that both converge by the limit comparison test. And you have to write a sentence stating that since this sum from n equals 1 to infinity converges because it's a p-series, then this right here, this series from n equals 1 to infinity must also converge by the limit comparison test. All right, we're going to knock out one of them from 27 through 34. I'm just going to pick a random one. I asked you guys to do all of them. All it does here is it says test for convergence or divergence. Using each test at least once, identify which test was used. So throughout this, you just have to pick a couple of them. First one, when you guys are looking at it, I see exponents. So I know that this is going to be the sum from n equals 1 to infinity of n to the 1/3 over n to the 1. I already know I'm going to use p-series for this because I see these exponents and it's n to some power. So let's go ahead and rewrite it. We're going to get the sum from n equals 1 to infinity of 1 over n to the power of 2/3. Right off the bat, p is less than 1, so it diverges. It's a p-series where n is less than 1 is less than 0. P cannot be negative, and it cannot be equal to 1. So this means that it diverges. Okay. This next one's geometric. You guys can tell from this right here. In a geometric series, if you have a number that is less than, if the absolute value is less than 1, then it converges. However, that is 4/3. So you're going to keep multiplying by 4/3. Things get bigger, so it diverges. Okay. This one right here, I see 5 to the n, so I'm going to go ahead and compare it to, 1 over 5 to the n, which is 1/5 to the n, which is geometric. In a geometric series where r is less than 1, converges. Okay, so now if I'm going to use the comparison test, the direct comparison test, I need to show that 0 is less than 1 over 5 to the n plus 1. I know that looks like an s, that is a 5 in fact. Is less than or equal to 1/5 to the power of n for all values of n. And what this means is if the larger series converges, then the smaller must also converge, So let's think about it. This right here, we're going to get 5, 25, 125. Down here, we're going to get 5 plus 1, which is 6, so it's smaller. That works for the first number. If I plug in 2, I'm going to get 1 over 26, which is smaller. This is always going to have a denominator that is 1 larger, so this is always going to be true. So it does converge by the direct comparison test, okay? And so you would have to go through and write something along the lines of, since 0 is less than 1 over 5 to the n plus 1 is less than or equal to 1 over 5 to the power of n for each value of n, or for every n of n, then the series from n equals 1 to infinity of 1 over 5 to the n plus 1 converges by the direct comparison test. Why did I put a capital T? I could fix that. There we go. All right. Let's go through and go to 70. And we'll take a look. If you guys want to do 32, 32 is telescoping. So keep that in mind when you do that one, okay? You're going to look back to your notes from the first section, okay? Or the second section. It's from 8-2, I believe.